Advanced metal alloys are essential in key parts of modern life, from cars to satellites, from construction materials to electronics. But creating new alloys for specific uses, with optimized strength, hardness, corrosion resistance, conductivity, and so on, has been limited by researchers' fuzzy understanding of what happens at the boundaries between the tiny crystalline grains that make up most metal. When two metals are mixed together, the atoms of the secondary metal might collect along these grain boundaries, or they might spread out through the lattice of atoms within the grains. Researchers at MIT have now found a way, using a combination of computer simulations and a machine learning process, to produce the kinds of detailed predictions of these properties that could guide the development of new alloys for a wide variety of applications. The findings are described today in the journal Nature Communications, in a paper by graduate student Malik Wagih, postdoc Peter Larsen, and professor of materials science and engineering Christopher Schuh. Whereas the atoms in a single crystal are arranged in an orderly pattern, so that the relationship between adjacent atoms is simple and predictable, that's not the case with the multiple tiny crystals in most metal objects. You have crystals smashed together at what we call grain boundaries. And in a conventional structural material, there are millions and millions of such boundaries, he says. These boundaries help to determine the material's properties. You can think of them as the glue holding the crystals together, he says. Creating new alloys involves trying to design those regions inside a metal, and it's literally billions of times more complicated than designing in a crystal. Schuh draws an analogy to people in a neighborhood. It's totally homogeneous. Whereas in a grain boundary, you still have something like 12 neighbors, but they're all at different distances and they're all different size houses in different directions. Traditionally, he says, those designing new alloys simply skip over the problem, or just look at the average properties of. Instead, the team decided to approach the problem rigorously by examining the actual distribution of configuration. In some cases, the clustering of atoms along the grain boundaries is a desired property that can enhance a metal's hardness and resistance. Depending on the intended use of an alloy, engineers will try to optimize the combination of properties. For this study, the team examined over 200 different combinations of a base metal and an alloying metal, based on combinations that had been described on a basic level in the literature. The researchers then systematically simulated some of these compounds to study their grain boundary configurations. These were used to generate predictions using machine learning, which were in turn validated with more focused simulations. The new database compiled from this study, which has been made available in the public domain, could help anyone now working on designing new alloys, he says. The team is forging ahead with the analysis. In our ideal world, what we would do is take every metal in the periodic table, and then the work was supported by the U.S. Department of Energy, Office of Basic Energy Sciences. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.